Hey everybody, welcome back. Hope you enjoyed your break. We've got a bunch of questions. Of course, we can't answer them all. Wish we could, but let's answer some. And certainly, any question you post, we'll be sure to get back to you with an answer. And we'll see if we can kind of find a way maybe to post these publicly as well too. Because my guess will be some of the people who are interested, others will be interested in the question and answer as well too. One of the big ones was this. It's like, hey Rob, where do I generate this correlation ID? And where our correlation ID is going to, again, be a unique identifier for each request that follows the request from end to end. That's a really good question. A lot of ways to do it, different approaches. Sometimes the client could pass a correlation ID in, and if so, that's fine too. But you can't count on the client. If you're exposing a service, you can't count on that client happening. So what we did in our example here, so we go back to our code, and I think we're in a good place here. If we go up to our API gateway here, and we'll talk about gateways in a moment. This is a front-end service. All traffic into the microservice application goes through the gateway first. If we look at an endpoint in the API gateway, here's one here. Here's our shopping gateway controller, shopping basket gateway. You'll notice the first thing that we do is we generate a correlation token. So if we're going to get all baskets, this is the endpoint for that, we generate a correlation token. If we're going to get a single basket, we generate a correlation token. The same thing here for get basket summary. We're always generating a correlation token first. And ideally what you would do, you might even say, we didn't do it here, but I think a good approach is say, if the client, usually the gateway is responsible for that, because the gateway is your first stop. If the client should pass in a token that you want to use, you might look for that in the header. So you say, if in the request header from the client, I see a correlation token, then I'm going to use that. If not, I'll generate my own. So here we're calling this correlation token manager. Simple class, lives under our infrastructure. What we did here, we have a shared service. We call it our Snowflake ID generator. That lives in our building blocks. If you go into, we've got a project called Snowflake. Very simple, really. So here's our Snowflake. Here's the generator ID right here. So whenever we want to generate any kind of unique ID, including a correlation token, we'll use our Snowflake ID generator. You'll notice in this case, we can generate a basket ID, a correlation ID, an order system ID, or a checkout system ID. So what we do, based upon the type of ID we want, we append what it is. We do a short date string and a short date time, and then we append all it together with a random number. So again, our particular ID or our token is intelligent. It'll say correlation. It'll have a short date, a short time, and a random number. So that way, we can look at one and it's human readable. It makes sense. We used to use a GUID, and you can use a GUID, but again, a GUID told us nothing. At least now our correlation token and our IDs have some intelligence to it. And by the way, the whole idea about Snowflake, that comes from Twitter. Twitter has a project called the Snowflake Project, and that's what they use to generate IDs. So it's a good read. Go look up Snowflake if you want. So basically, we generate our IDs in, let's go back, into the, where are we here? Let's go back. In our API, in the front-end API call, and then we pass this correlation token along. You see here, we're making a call from the API controller. We're going to use, we have an API library here. We call it REST client. And notice we're passing in the correlation token. In our API library, we take the correlation token and we basically put it into a request header. And then what happens then is the gateway controller calls the back-end service controller, in this case the shopping basket controller. We take the correlation token out of the header, and then everything we do, I'll give you an example here. So here you can see when the shopping basket calls into the, let's go to services. when it calls into the, where's my basket service? Right here. Notice the basket service controller. Okay, this is the back-end service for the shopping basket. Notice what happens here. When this comes in, right? First thing we're doing, so here's my get basket based on an ID. Notice as well too, we're using some really nice plumbing from .NET, from .NET Core. We're saying, here's my from header. Go pull out the correlation token. This is the actual header, request header, and stuff that into this particular value. So .NET Core makes this extremely simple. In the call from the API gateway, we stuff the correlation token into a header with the name X correlation token. And then in the backend controller, we just yank it out. We use a from header attribute to do that. So now we're in the backend service. We have the correlation token. We make sure it's there. And notice when I call the backend business service here, I'm passing the correlation token in. So when I call my business class, again, the correlation token always follows the request. So if we go in and look at that here pretty much, you can see, here's a good example here. Let me find one that shows. So here is a add in the basket. We're passing the correlation token in. You can see wherever we make any kind of call to anything, we're all here. Notice we're calling the Redis repository. So here's where the shopping basket is talking to the Redis cache. We're calling a get basket async method, and notice we're passing the correlation token in. Why are we doing that? Because in the Redis repository, we have logging, we have error handling. If anything goes wrong, we're going to include the correlation token. So we can always, again, say, here's a correlation token, filter all the logs on that value, and then we can pretty much see an end-to-end flow, if you will, of that particular request. Here's some times as well too. So as we're going through the different modules, we basically clock the actual time and send that back as well. So that way I can basically say not only do I know the route, but I can actually see how long I spent in each area. If I'm spending 10 seconds in something, that would be a big red flag. I got some kind of bottleneck there.
So
again, that would be, sure.
Yeah, so as we're looking about, and you're talking about the correlation token, there's a couple comments that are coming in on chat that I think make an interesting point here. We're receiving this correlation token, which feels like it could be a piece of middleware. For the purposes of the architect, for the purposes of the business logic of our application, the correlation token is really a piece of architecture concern. So while we're doing a nice job here showing here's passing the correlation token along, it feels like there might be a place where, when we receive the correlation token, maybe there's a filter here in these controllers, in these services, to take the correlation token in that on action is executing and stuff it into our repository pattern so that the repository pattern has it and carries that along for us.
I love that thought. That's a great thought. You know what? We're not doing it here because we want to be able to show it, but that would be precisely what you want to think about doing as well too. Abstract it away, put it in the middleware. There are a lot of good open source examples out there. I can find one that I was looking at about 6 months ago. Somebody already did that. And I actually had his code in here, but then we took it out because again, we wanted to demonstrate the concept, right? That's an excellent point. So I think as you evolve, as you build these things out, you find, not only, what can we take and what can we abstract into the underlying middleware?
Yeah,
then to make it an architectural consideration.
Your get basket async you were pointing out there on line 99 becomes just get basket async basket ID. If we're stuffing the correlation token in somewhere just outside of our controller here. So
yes, we are.
Great points there from folks in the chat room. There it was line 99 we were looking at.
Right here. So again, we can do this, but like you say, if we can abstract that away, much better idea. Because we know that every request is going to have that pretty much. So if we can do things to sort of abstract that and make that, because again, that way we're not forgetting to pass it in as well too. So
Yeah.
definitely agree.
And it
Great
becomes
point.
easier to mock
Great point.
as later on as well. So
Exactly right. Again, keep in mind, in training applications, sometimes we'll do things longhand because we want you to see what we're doing here. But that's a
really make it
really, really good point.
obvious, all the concepts that are happening.
Yeah,
Yeah.
exactly. But like you say, as you begin to architect these things, you say, what can we hide? What can we abstract? What can we automate out of this, right? So we know it's there, but we're not having to deal with it. Perfect. Great, great thought.
And Samir here in the chat room says, when you're using an I repository, should not be the abstraction over whether it is Redis or some other type instead of a specific type. No, Samir, you're absolutely right. Yes, when we do have
Agreed.
an abstraction, we're naming it Azure Redis repository here so that you know that's what's coming through. But in practice, you want to be able to swap out between Redis or other, maybe you want to use SQL Server, maybe you want to use another event store, maybe you want to use MongoDB or Cosmos. We can make
really
that
good
interface
point.
simpler.
So here's my Azure Redis repository. If you think about it, there's nothing really Redis about this in here. So yeah, absolutely. Again, we did this to keep things simple, but this should really be just like iCache repository or whatever, our repository. And again, then we can plug in, like you say, we could name our concrete type Redis. But again, yeah, excellent point, Samir. In fact, we're going to change that too. Thank you. Okay, great. You guys are good. Keeping us honest. We love that. Let's keep going. Let's talk a little bit now about Jeff. Anything to say?
I was going to say there is a question here. One more question that I think we may have answered here. Niyoashi asks, can we pass an ID from a client app, say JavaScript, SPA, or maybe Blazor, into the API, into the database, publish integration events, and then further into event handlers? I think that's a little bit of what we saw there, where we were putting the correlation ID on as an HTTP header as we were making requests from service to service to service.
Yes, and I think it's a really good idea. So again, you may expose the application to a number of different clients, and some of the clients may say, you know what, I already have a correlation ID. It'd be very helpful if I could pass my correlation ID into the service and have the service consume that. And again, we should always have the capability in our middleware coming in to we say, if we basically specify if you want to pass a correlation token in a header, here's the key to use, right, for your key value pair. If we see that key, we're going to use yours. If you don't pass one in, then we're going to go ahead and generate one, and we'll use our own. That's an excellent point. So that way you're covering both bases. Mm-hmm. If the client passes one in, great, we'll consume that. If they don't, then we can generate our own and log anyway. Great point, by the way.
All right, I'll step back.
Great, thanks a lot, guys. Really good questions too. Please keep them coming. Again, the ones, I know there are many. We will get back to all of you on that. So let's talk about communication, because again, a large challenge, like we said earlier, to moving to a microservice-based architecture is communication. So, we'll talk about really two aspects of it. We'll talk about front-end client communication. How do our mobile apps and our web apps and our desktop apps communicate with microservices? And then we'll move into the back-end service communication. How do back-end services do that as well too? Here's front-end. So you think about front-end clients, typically distributed applications, microservices pretty much, expose themselves, if you will, kind of a bad play on words, to decoupled front ends. Typically the front end is not part of the microservice. So we could have a mobile application, here's an iPad tablet application, we could have a web application, the desktop version. So when we have these independent front-end clients, what communication patterns come into play for talking to back-end microservices? We typically see two varieties. One is a direct client communication pattern, and the other is something called the API gateway. Both are commonly implemented with REST over HTTP, what we're seeing is gRPC is gaining popularity as well too. And we'll talk about gRPC and show an example of that a little later as well. So again, these front-end clients typically are going to be talking to either the services directly or to this gateway component, typically using HTTP, or nowadays, and we'll see more and more gRPC on that. So here's the direct client communication model. Here's our application. Here's our device, right? And notice it pretty much has exposure to all of the, direct access to all of the back-end services. So again, this is pretty simple to build, right? We can have a simple REST library, and we can make direct calls to each of these back-end services. But this is not typically done in building out these applications. This is far from ideal, if you will. A lot of problems with this direct client communication. For example, the client is tightly coupled to back-end core services. So that would mean any kind of refactoring or partitioning of our back-end service could easily break the front-end client. So that's not going to be a good story for the client. Here's a problem too. Now the client becomes chatty. For example, maybe if the client wants to add an item to the shopping basket, maybe the first thing it needs to do is call the product catalog and say, hey, do a product lookup on this ID. What is this item? Then the client says, I need to call the inventory service, see if we have any of these products to even sell. Then maybe the client needs to call the shipping service to get a shipping date. And then finally, then it says the fourth call might be to actually add the item, aggregate that data, and add it to the shopping cart, and then send you a response back saying, we put your item in your shopping cart. Again, we got to be careful with this, right? A couple things. If this is on a broadband network, this is going to tend to be slow, right? And now we got to be careful here because now we're putting business logic and orchestration logic in our client. We typically want to keep the client simple many times. And what happens with these types of applications is the client will change much more frequently than the back-end services. So again, we want to kind of try to keep the client as simple as we can, and keep the back-end business logic on the actual services when possible. So another big problem here too is that in this scenario, each one of these services has to have a full set of cross-cutting concerns. So product catalog needs a full set of cross-cutting concerns, as does the review service, as does the order. That gets to be complicated here. So, and one more big thing, look what's going on here. Anybody see this? There's a security concern here, isn't there? Our front-end client has direct access to back-end services. We're exposing these back-end services to the front-end client. We're widening our attack surface. We really want to do that. So again, while we can code, or we can build this simple direct client communication, it's not often done in practice. Instead, what we see is this. We see something here called the API gateway pattern. This is basically where this is where we build an intermediary service. It's another microservice. It's a gateway here pretty much. And it acts as a single point of entry for all of the client traffic into the back-end services. So the clients only know about the gateway. They have no idea what's behind it pretty much. The gateway insulates the clients from the back end, and the gateway also insulates the clients from internal refactoring and partitioning of these services. So if we're making changes to these services, many times we can catch that change and adjust for it in the gateway without breaking the client. We may at some point, for example, say, you know what, we're going to take microservice 1 and break it into 2. Maybe it's not granular enough, or maybe we're going to take 2 services and put them together. Whatever we're doing, we can typically adjust for that change in the gateway without constantly breaking the client as well too. A couple of rules here. So again, remember, the client primary responsibility it's like a reverse proxy. It receives the request and it's responsible for routing it to the back end services. A couple of thoughts here. You typically want to keep the gateway close to the back end services, right? So if we're running in Azure, for example, we probably want to have the gateway and the services all in the Azure network. So the client makes a single call to the gateway, And then the gateway is already in the Azure network. So when the gateway is calling back-end services, it's going to all be in the same network. It should be much faster, much less latency, if you will, too. And keep in mind the gateway as well, too. We don't want it to become a single point of failure. So here we're going to need availability. We're probably going to end up with multiple instances of the gateway with a load balancer in front. We just don't want one gateway. We want to keep the gateway lean, mean, and keep it available. The gateway needs to be simple. We don't want to load it down with a lot of business logic. And we want to make sure that we have more than one instance. So if one of the instances should fail, the load balancer takes it out of rotation, routes calls to the other instances while the Azure Fabric is fixing that instance. When it comes back online, the load balancer begins routing traffic back to it as well too. So again, this is the API gateway. We got a front-end service, if you will, and it pretty much is responsible, if I can get back to it, for pretty much abstracting away the back end on this. Here's a problem though. What you want to always think about for larger microservice applications, you want to beware of an overly ambitious gateway, especially in a large system. So if we have a lot of back-end microservices, and if we have a large number of different types of clients, we might come to the conclusion that a single gateway becomes too much of a bottleneck. So we might want to think about a pattern called the back ends for front ends pattern. All that really does is it says, you know what, instead of exposing one gateway, I'm going to expose multiple gateways. Same set of services back here, but I'm going to segment my gateways. I'm going to partition them. I'm going to have more than one. So in this case, we may have a gateway that basically handles all of the web app traffic, another gateway that handles all of the iOS mobile traffic, and maybe a third gateway that handles all of the desktop traffic. Even though we're talking to the same services, these gateways are basically partitioned for a single type of client. And they also think about this. The iOS will probably expose less granular calls and data than will the web app, which will expose more. And then the desktop will probably expose even more functionality than even the web app. So again, we can have different functionality exposed, if you will, different data exposed from these different gateways, all talking to the back-end services. So we could segment these things by again, user experience, web apps, mobile apps, desktop apps. Maybe we could segment them by service category. We could have one gateway that might take care of the inventory and the shipping service, another gateway that might deal with the shopping basket and catalog. So again, however it makes sense, but the idea here is we're breaking up the gateway so we have more than one. Because again, we want to keep the gateway very quick, very fast. We don't want it becoming the new monolith, if you will. Another pattern that we see with gateways is this. It's called the API Gateway Offloading pattern. So by having this gateway, it gives us an opportunity to offload some of the back-end cross-cutting concerns. Not all, but some can go away. So for example, if each service has a full set of cross-cutting concerns, could we not maybe begin to offload maybe the service discovery, maybe the correlation token generation, the caching, the resiliency, some of the metering and throttling from the back-end services, moving that to the gateway. So we're making the back-end services more simple, and the gateway becomes responsible for doing these cross-cutting concerns as well too. That's something we commonly see done as well. I mean, there will always be some cross-cutting concerns in the back-end gateways. We're always going to authenticate. We're always going to log. We're always going to authorize. But we can move some of the other stuff, things that are going to be more client-centric, to the front-end gateway if we wanted to. Again, the caching, the resiliency, the metering, great places on the front, on the API gateway. So your question would be this, and again, I'll show you that we built a gateway to keep things simple. When we built this reference application, we wanted a very simple gateway. So we went out to GitHub. I think I typed in API gateway. I filtered on C#, and there were many, many, many examples to look from. So we built a very simple gateway here. We're not doing much in ours. Again, all calls come through this project right here. This is the API gateway service. Everything comes through here. You can see each back-end service has a controller in the gateway. So here's our basket gateway controller, our catalog, our ordering gateway controller. And again, each endpoint in our backend services has a corresponding endpoint in our API gateway version as well too. So what are we doing here? Pretty much we generate a correlation token. We have a REST client. So instead of having all of the REST, we're using HTTP client. So instead of having all of the different configuration settings, we can put everything into a REST client, and we can call that. So we can sort of abstract that away. We make the call, we get a response back, and we're able to either return, we do some logging, and we can pretty much return, whatever we need to return back to the client here. A success, or in this case, this is going to be a failure. So again, we got a very simple gateway here. We're not really doing much, but you would probably, in your production application, want to think about something a little more robust than that. But the question becomes really, how do I get a gateway? Well, one of the ones you probably would want to look at if you're in Azure, there's a service in Azure. It's called Azure API Management. This is a managed gateway service in Azure, very robust. It's not free, you pay for it, but again, it has a tremendous amount of functionality that would probably make life good for you, much easier. This is what it looks like. It is a gateway itself. It has several components. It is an API gateway, you see right here. It handles the inbound and outbound traffic right here. It also has a developer portal. So you as a developer, you get access to certain services that exposes, and you can go into the developer portal, and you can pretty much see your services. You can get a robust description of what that particular service is. You can see what the actual parameters are, the endpoints are, what the return, the payload looks like. You can get an idea of the status codes that'll come back. Very similar to what you might see in Swashbuckle or Swagger. You can try it out, and you can also have the developer portal generate stub code. So you might say, I need to use this service in my Java application, or I need to use this service in my .NET application. You can have the developer portal generate stub code for you as well. So again, a very rich developer experience in the API gateway from Azure. And there's also a publisher portal as well too, where you can pretty much publish services. You can configure what we call policies, we'll talk about in a second. You can really publish and configure the things as well too. So again, a really nice one-stop API gateway that's in the cloud, managed by Azure. It's fairly robust, so Azure API Management, it can expose services not only from Azure, but you can also expose on-prem and even service from other public clouds, all through this API gateway. So it's not just Azure. You can have on-prem services, you can have exposing services from other clouds as well too if you want. There's also a really interesting feature. It's called policies. So in Azure API Management, there are a large set of pre-built policies that you can enable to affect behavior. So you can enable these policies, and you can apply them. You can apply the policies to inbound calls, to outbound calls. You can invoke them on an error. Lots of built-in policies. There are ones to restrict access, policies to throttle calls, policies to enable caching. There's a policy, I believe, to generate a correlation token. Or you can control the flow of the service. You can transform data. You can even craft your own custom policies. So instead of writing lots of code to do these things, you can enable the policy and configure it, and pretty much it will then be in effect for your inbound, outbound calls into and out of Azure API Management, as well as your errors as well too. So again, something to look at, API Management. There is also something here called Oscillate. Oscillate is an open source .NET Core API gateway. It's been out there for quite a while. It's used quite a bit. We looked at it about a year and a half ago. I think since then it's come a long way. Lightweight, it's fairly simple to use. It is scalable. It exposes a lot of different features: throttling, logging, tracing, load balancing, request aggregation. So again, this is rather an open source one you can plug in. It does work. eShop, the other reference architecture from Microsoft, it uses Oscillate as well too. If you go out to Oscillate in the browser and just type in OC Let's take a look here. You'll see it. It is an open source project. Quite a few contributors to it. The oscillate gateway. Here it is here. Again, here's the code for it to use. And here is some of the documentation as well in here. Documentation for it as well too. So again, something to look at here. It's so that is one more thing to think about too before we get off this with front-end traffic. I want to come back and talk about this. Another option as well too that you might think about with front-end clients would be more of a real-time communication. So again, we talked about this yesterday in the conference, but there's Azure Signal R service is a fully managed service that simplifies real-time communication in your web-based applications. So again, what it does is it abstracts that complex plumbing from you registering, an endpoint with the service hub, okay, Signal R hub, and then having messages pushed to you. You register your client, and once you do that, then pretty much the server can push data directly to you. You're not having to poll the service all the time. So again, if you want that real-time experience, Azure Signal R would be something to look at for that. Again, managed service is in Azure. Again, it hides a lot of the ugly plumbing that you would have to do to make all that happen. So again, that is really front-end client communication. We talked about direct client communication. Probably not something you're going to do very much, but we talked about using a gateway. We talked about what gateways do. We talked about a couple of patterns with gateways. Any questions, comments on front-end communication?
Hey, Rob. Can you hear me?
Sure can. Yes.
Oh, fantastic. So there are some questions here. And you know what? Somebody said, hey, what about Signal R? And you went right back to it when they asked that question. So that was
magic.
really good
There
to
you
see.
go.
There is a question here. We've been focusing on web-based apps. What about mobile apps?
Yeah, same. So like a mobile, and I think in that context, you're probably thinking about a mobile front-end client talking to a web-based microservice application.
Yeah.
I think we're talking about a mobile client. Yeah, it'd pretty much be the same story on this, I believe. So we would say pretty much, let's go back actually to our original gateway side. So even in here, here's our gateway, here's all of our back-end services. Again, the different types of clients consuming the gateway, it could be a browser, but these days very well likely being a mobile application as well too, consuming the client. And what's really interesting about a mobile client as well too, we could probably, instead of using HTTP, we could probably think about using GRPC as well here too. We'll talk about GRPC in a little bit. There is finally browser support for GRPC from .NET. That's relatively new, but I think there's been GRPC support for mobile clients as well too. So instead of sending RESTful HTTP calls, we could think about doing your GRPC. But definitely, the gateway again says, you know what? I don't care what kind of client you are. Send me your requests, whether they're HTTP based or whether they're GRPC based, and let me handle them for you. Good question. Any other questions, or do we want to move on here?
Yeah, let me take a look here. A lot of folks are looking for links to the code and the slides. I know we were planning on putting them. There was a specific place we were looking at putting them to go with this. If we can share that during the next break, I can try and get that shared out to a GitHub repository to at least get it in our hands. The hands of
sure.
Right now.
Sure. That sounds great.
There was a question about Azure Front Door and about using API Gateway versus Azure Front Door.
Good question. You know what? Let's mark that question, and we'll get a response to that. I've just started looking at Front Door, so hold that question, and we'll come back to that.
Actually, we'll
publish that one.
It sounds like Manu, you had a.
Go right ahead, Manu.
Can you hear me?
We got you
perfectly.
Oh, awesome. Yeah, no, absolutely. That's a good question. And we do have quite a few products, right? Rob mentioned API management. We also have an Azure Application Gateway, which people can use. It supports Ingress for Kubernetes now. And similarly, Front Door is obviously kind of a gateway, and it can do some of the layer 7 stuff. So yes, I mean, we have quite a few options there to kind of front your Kubernetes applications, for example, to serve as those gateways. And I'll kind of go more into some of those details as we, get into the Kubernetes and we talk about some of the ingress.
Yeah, that's a good place for them. Here's a slide that I didn't show you, but it's in the deck. I do have one on Azure API or Azure Application Gateway. This is not it. Keep in mind, this is not Azure API Management. Again, hey everybody, sorry about that. We had a little bit of a technical issue. But let's come back. We're talking about microservice communication. We're talking about how back-end microservices communicate with each other. And this is a pretty key area. So we said there's really two ways microservices can communicate with each other. Okay, they can use either a synchronous request response model, or services could use more of an asynchronous publish subscribe model. So we're going to look at both. The question you might have would be this: when do I use a synchronous approach from an asynchronous approach? And I think the answer to that is it depends on the message type. So when we're dealing with microservices, we're looking at three different kinds of message types. There could be a query. A query basically says, I'm service 1, I need service 2 to do something, right? And I can't complete my operation until I get some data from service 2, or I get service to do some kind of operation. So I'm dependent on service 2. That's more of a query, right? How about a command? A command says, I'm service 1, and I need service 2 to do something, but I don't need to wait around for it. I just need to let service 2 know to do it. And there are also events. I'm service 1, something has happened, there's been some state change, and I'm going to publish an event of that state change, and I'll give other services the opportunity to respond to that event if they want to. So again, those are the three primary message interaction patterns that we see in services. Query, I need something. Command, I just need you to do something when you get around to it. Or an event, something has happened. Let's talk about all three. Let's talk about query first. Query is the tricky one. So again, queries are always going to be synchronous. So here again, here's a calling service, service 1. It needs something from service 2 to complete its operation. It needs data from service 2, or it needs service 2 to execute some kind of operation before service 1 can complete everything. So what happens here? Service 1 comes along, it opens up a connection, it makes a direct call to service 2, and basically waits. Service 1 waits, while service 2 is processing the request, and then one of three things are going to happen. Okay, hopefully, ideally, service 2 will send back an immediate response with the answer service 1 needs, and service 1 can complete the operation and be done. Or service 2 could send back some type of status code that would say this was unsuccessful. It's a 404 status code. It's a 500 status code. It's a 408 status code. That's not going to be a good scenario. Or service 2, thirdly, it could say, you know what, I timed out. I'm not sending back a response at all. So again, service 1 needs to be careful here. Okay, a couple of things to think about here. Number 1, service 1, when it makes this call, this is synchronous, we're probably going to want to do this. We're probably going to want to put an async await pattern so we can release that thread while that call is taking place. So that thread can do other work. And then by using the async await pattern, we will implicitly put a call back in. So when that call comes back, we'll grab a thread on service 1, and then we'll keep executing it. Oops, I wanted to do this. We'll keep executing it for you. That'll be great. If service 2 begins to pass back bad status codes or it times out, we may, at that point, based on the status code, need to retry that service a couple of times. We'll talk about retries later. We retry because many times when we get back a bad status code, it's very short-lived, very temporary in nature. But then you can see the problem with the synchronous code here. Okay, we're blocking. We want to release the thread, But again, this is always going to be synchronous here. That becomes a problem. So what about this here? Look at this here. Here's a scenario. I'm a user. I'm using our online music store application. I want to add a song. So what do? I pretty much I want to add this song by Charlie Daniels. I think he just died. So I want to buy a Charlie Daniels song, right? So I basically say buy the song. I click buy on the or my add to shopping cart on the web app. It sends a message to the API gateway that says add item to basket. The gateway routes that call to the shopping basket microservice on the back end saying this user wants to add this song from Charlie Daniels to the shopping basket. The shopping basket goes, hang on a second. You know what? I need more information about that song. I have this ID, but I need to call the product catalog to do a lookup on that song. So what does shopping basket do? It makes a direct synchronous HTTP call to product catalog, and it sits there and it waits. It waits until product catalog returns the information about that song. Again, hopefully it's milliseconds, but it might not be. Once that information comes back, then shopping basket goes, this is great. I know what the song is. I know who the artist is, all that good stuff. Now shopping basket needs to make a call to discount service to say, for this user, is there any kind of discount? So this isn't really a lookup on service or on data. This is going to be a computation. So shopping basket makes a direct HTTP call to the discount service, passes in the song, the user, so and the discount service figures out whether or not there's any kind of discount for this user. And what does it do? It returns eventually a response back to shopping basket. At that point, shopping basket adds the item, sends a response back saying, hey user, we have put the Charlie Daniels song in your shopping basket. So what's going on here? Anybody see a little bit of a problem here? So now what used to be remember we said this was an independent, self-contained microservice, has its own data, has its own dependencies, pretty much, it can evolve frequently, deploy independently. Well, now it has dependencies, right? It's dependent upon the product catalog service. It's dependent on the discount microservice. So again, life is, so now we're beginning to reduce our autonomy, and we're beginning to lose some of the architectural benefits of a microservice application. Here's a problem with this, okay? This will impact performance. Even if it's quick, this is going to add latency onto the call, making a network call to product catalog, a network call to discount is going to slow things down dramatically here on this, right? The problem really becomes if you have one of these a minute, probably not a big deal. If you have lots of these, say many per second, this is going to become problematic. Another problem here is reliability. What happens if one of these services is unresponsive? It's backed up, it's slow, there's some kind of network transient fault going on. Again, this is, this is going to, anything unresponsive is going to impact the entire operation of the service. So we need to be really careful when we begin to couple these services together, with this direct synchronous communication. So again, approach with caution. Many people would say don't do these kinds of calls. They're not a good idea. We say approach it with caution, especially when there's high volumes of these kinds of calls taking place, right? Here's a real problem with this though. This particular pattern here, this can lead to long, complex chains of synchronous calls. Look at this. What happens when this happens? This is a little contrived, but we see customers doing stuff like this here. So here's the user. They want to check out. They basically check out on the web app. That goes to the gateway. The gateway sends the checkout message to the shopping basket. Look what happens here. Shopping basket does a direct HTTP synchronous call to product catalog, which then does a direct HTTP synchronous call to pricing engine, and in parallel, another direct HTTP synchronous call to ordering. The ordering does direct HTTP synchronous calls to shipping, to inventory, to customer. Again, contrived, but this is getting kind of crazy now, right? Even if this works well, this is going to take some time to execute this. What happens if 5 is slow? How do we respond to that? What happens if step 7 isn't responding at all? How How do we recover from this, pretty much? Again, this can be very private. This is not a good idea. So again, these deep chaining or nesting of HTTP calls, not such a good idea. This would be a clear anti-pattern when building out these things. I like to think about this picture right here. Deep chaining of microservices. This is kind of what you end up with, I think. Many industry blog posts point to deep chaining as a reason for failure. Look up Jimmy Bogart is an excellent resource in the community. Look up his a presentation, a webcast on a microservice nightmare, and it was this very problem. Again, he talks about it. But be really careful getting into these kinds of scenarios. Even this scenario isn't a good scenario either. Again, synchronous calls across microservices. So you might say, well, what's the answer to this, right? How do we get around it? Well, different approaches. One thing you might want to think about doing is this. You might want to think about maybe building an aggregator microservice. So if we know an operation to add an item to a shopping basket consists of calling the product catalog, calling the discount. Maybe what we do is maybe we have a separate standalone microservice right here, this one in purple. We call it the add item aggregator microservice. It's responsible for orchestrating that call. When the gateway goes, customer wants to add an item to the basket, it invokes the add item microservice. And the add item microservice, this has basically the orchestration of the workflow to basically first call this, then call that, and finally put the item into the shopping basket. Again, these are synchronous calls. We're doing HTTP here, but we're centralizing everything into a single location. And again, this particular model is going to make it a whole lot harder to do that deep chaining that we just saw before too. So again, this is a common pattern using an aggregator microservice. Again, we'll talk about, keep in mind too, we're doing HTTP, but we'll talk about doing GRPC in a little bit as well too, as our protocol. Another one could be this. If we really wanted to get complicated, we could say, what about a request reply pattern? This might be sync over async here. So what does that really mean? So here we have this shopping basket service. In this case, it needs to call the pricing microservice. If we really wanted to make these asynchronous, we could think about putting a input, I'll call it a request queue and a response queue in place. So here comes the post, maybe. So the shopping basket goes, I need a price. It could place a message into the request queue saying, I need a price for product 557, and here's a correlation ID, unique value for that ID. The pricing service could grab that, pull it out of here, compute the price, shove a message back in the response queue that would basically say the price is $3.98, and here's that same correlation ID. And then the original service could pull the response queue, pull the message out, match the correlation ID and say, oh, the price for 557 is $3.98. So this is done sometimes. You'll see it referred to as sync over async. You probably don't want the client waiting, but if you had, in this case, maybe your signal R in place, we could basically execute the operation and SignalR could send back a price from this. But again, this is one way that we might think about decoupling that communication, all as complex as it gets here, pretty much. Another way we think we might do, if we absolutely positively have to do a synchronous call, do we really want to use HTTP? What about GRPC? We talked about GRPC yesterday. That is a high performance, highly scalable, open source, general purpose remote procedure framework. It evolves the RPC that we're used to see. When we did WCF and SOAP and all that pretty much. The G stands for Google. It originates from them. It is now open source. Let's talk about gRPC. Let's do this. Let's take a quick break. Go back to the book. Here's the book that I talked about earlier. We're going to type in Microsoft Architecture. It's already there. Cool. We'll go to the guides. We're going to go to the Cloud Native book here. Again, a lot of what we're talking about right now is in this book in detail. So if we go to the communication, sure enough, here's gRPC. So we talk about what gRPC is, so on and so forth. But look at this here, gRPC benefits, right? gRPC uses HTTP2 for its transport protocol. So what does that really mean? Well, that means HTTP2 pretty much says the actual data transport is going to be binary. So instead of passing text messages back and forth, we're passing very small, streamlined binary messages, much smaller, much quicker. And even more so, HTTP2 gives us access to multiplexing support. So with HTTP 1.1 and REST, we're basically passing one request and one response on a connection at a time. With HTTP2, we can basically multiplex. We can send multiple parallel requests on the same connection. So you get a lot more out of it. We also get bidirectional full duplex communication. So you can basically send and receive client requests at the same time. And what's really interesting too is we have built-in streaming. So if we're basically making a call and getting a collection of data back, we can have that data streamed to us. So instead of pulling it back, pretty much it's being pushed back by the service very, very quickly. So again, gRPC is very interesting. Now these figures will be different, but what I found when I wrote this pretty much, some of the literature I saw, people were claiming gRPC to be up to 8 times faster than JSON serialization. Well, that's pretty quick. If it were 4 times faster, that would be huge, get alone 8 times. With message sizes being 60 to 80% smaller, well, if it were 30% smaller, that would still be huge. So again, you probably want to look at gRPC. I think you'll see a lot of it in the future. I'm going to show you an example of it right now in code. .NET 3.0 and above, we have built-in support for it. So let's look at gRPC real faster. So in the application, let's close some of this stuff here. We do use gRPC. We have, I'm going to close all the documents for right now. Perfect. Now we go into this guy. You'll see, let's do this. We have an API gateway service here, and then we have a ordering service over here. So we're primarily using HTTP for calls across. What we did do, though, is in the API gateway, the calls that we make to ordering, we basically rewrote them, refactor them into gRPC. So what you're going to basically see here in the controller is we have a gRPC client service. So the API gateway becomes the client for our gRPC call, and then the server, think client server, that's going to be our ordering service. It's going to have our ordering, where is it? GRP ordering service. Think of this order gRPC service sort of as a controller, if you will, on this. So again, we implemented gRPC in both of these projects. How did I do that? Okay, the first thing I had to do was this. I had to come up with something called a protobuf file. So in gRPC, there's something called a protobuf file. I'll show it to you right here. This is sort of like a wisdom file. If you think about WCF, this basically describes pretty much the operations and the data in the operations. So here's my proto file right here. I called it ordering dot, it has a proto extension. So you can see in here I've got 2 operations. I've got one here called get order, and I got another operation or endpoint called get orders, right? And you can pretty much see the get order accepts a parameter, I call it order argument, and it returns an order. And then the get orders, it accepts an empty argument. Notice how I have to use an empty argument. I just can't use a spacer. And then it returns a, ooh, look at this, a stream of orders, right? So these are the 2 calls right here. Notice, again, here's the RPC keyword in here for these things. So what is this order argument? What is order, orders, all this? So we have beneath it, we have a message. So this message here, this represents this order argument here. This becomes a class. So I actually generate a class called order argument proto. Everything is proto, just to suffix it. That has basically a property called order ID. I got another class. This is like a DTO class called order proto. And again, this gets generated by the .NET framework. We call it public class order proto. Has an ID, an order ID, a date, shopping basket, so on and so forth. Here's my order detail, and here's my orders. So these are my data classes. Notice when I say an order has an ID, a shopping basket ID. It also has a set. Notice this repeated keyword. So an order has a collection or repeated of the order detail. So a collection, each order detail has the ID, the album, quantity, price, so on and so forth. So pretty much this file defines the actual operations, the get order and get order, and it also, I don't know why this is even, I think I'll turn that on. It also for me, because I see, let's close this for right now. I'm going to close Teams in the background. We don't need that on. I'm going to see a lot of extraneous stuff in here. Perfect. And these are all the data for it. So I had to put this ordering proto file in the actual ordering project. Now, what's interesting about this order proto file, this particular file is basically cross-platform. The only thing that's Microsoft core-centric will be line 6. I'm saying that the namespace is going to be the ordering API proto. So this would be different in Java, different in Go, but everything else, pretty much, this file it's not Microsoft specific. Notice I'm implementing some namespaces from Google for the timestamp and for the empty proto here. Again, this file lives not only in the server, which is the order, which is going to serve up the orders, but my client, the API gateway, it too also has a copy of the order proto. So both sides have a contract, if you will, of what the particular operations are and what the data is going to look like. What's interesting here now is when I build these projects, .NET, the actual engine, is going to take this proto file and it's going to generate some plumbing classes behind the scenes for me. It's going to generate these, basically a class with these operations, and it's going to generate DTO objects for each one of these proto message types. What I had to do though is this: I had to basically tell .NET Core, I had to say, hey, .NET Core, for the API gateway, this is going to be, for this proto file, this is going to be the client. So how did I do that? I had to go into the project file for API gateway, open it up, easy to do. We find it in here. I had to say, where is it in here? I had to say right around, so in the project file for API gateway here, I had to add what is called an item group, simple to do, item group of type protobuf, and I said, hey, API gateway, the proto file lives here, proto / ordering proto, there it is. And here's the important part. I had to say .NET, this is going to be the client, so generate the client code for me. So here I'm telling .NET Core that this is going to be the ordering, this is going that we're going to use gRPC, and that the API gateway is going to be the client, generate the client code for me. In the ordering service here, I had to open up that project file, go down and create another item group. Same thing pretty much. You could just copy and paste this. The difference becomes this though. Item group, the same include, but now look at this here. Now I'm saying a gRPC is equal to server. So I'm saying this order API gateway here, this is going to be the server. So by putting server here, when .NET Core, when I build the project, we're going to generate in the background the server code. Here's what it looks like. If I were to go into I'll start with server. If I go into the server and right click, and if I say go to where is my File Explorer? There it is, open File. So I'm going to open up Ordering API in File Explorer. Maybe. Here it is right here. So here it is in File Explorer. This is the ordering service right here. Look at here. If I go into the OBJ folder, if I go into debug, ooh, this is the publish code here, isn't it? Look at this here. Look what .NET Core generated. It generated an ordering class and an ordering gRPC class. This is the plumbing code, if you will, for gRPC for the server side. If I look at it, this is what it looks like. You might guess it's kind of ugly, so you're probably happy that it gets generated for you. It's what it looks like here. You can see all the magical goo in the background going on. Close into this stuff. You can see in here, bind service. There's actually two classes. This is the easier one here. We go into the other one. Let's go into the ordering class really quickly. You'll probably see a little more here. Here's the ordering service. Let's look at that. Yeah, you can see more in here. You can see, if you begin to look through, you can see the actual methods are in here. There's a lot in here, actually. Here are the different properties that are exposed. Calculate size. Here's your order proto. Again, this is all plumbing code that gets generated for you, so you don't have to even deal with this. But this pretty much enables the ordering API to be the server for this gRPC call. You can see this is pretty long.
Yeah, Rob, I was going to say, can you zoom in just a little bit there? Folks can't really see it. I know we don't really care what some of the content is.
Oh, sure.
They can
Absolutely.
see a little bit better.
This is kind of what it looks like here, pretty much. There's a lot of, you can see, you know, the attributes. This is the merge from, again, a lot of, let's go down. I'm going to arrow down to maybe a good part. So now you can begin to see the properties. So if you look here, here's like, here's the album ID property, public getter and center. Above it is the order ID. So you can see how we're basically building out, how the engine builds out all of the properties for the different things. So we get into, you can actually get down, eventually get into the methods as well here too. But again, a lot of the plumbing code, stuff you probably don't even want to see. But this gets generated for you. This is generated again, this is a server code because I told it to. If I were to open up the API gateway, I would see the same files, but there I would see the client code, not the server code, because I told API gateway in the project file, I said generate client for me. So now that I have both of that, again, when I build the project, the plumbing code gets generated for me. So what I have to do now is in my project, here's my, for example, here's my ordering client. I need to hook into that code that gets generated, that strongly typed client code here, in order to be able to use gRPC. You can see here's the gRPC client. I'm calling a .getOrder method on it. This behind the scenes is invoking the plumbing, making that call to the ordering API. The ordering service grabs it. The plumbing code grabs it there, and the service code generates a class which I inherit. And then from that base class, I'm able to call to get the get order. And you can see I've got the get orders here. The get orders is kind of interesting here. This is the actual gRPC server class here. Not a lot of, it's not very fancy really. One thing I am doing now, you can see when I get the orders back from this is coming from a Cosmos DB database. What I do here though, when I write these things out right here, I'm streaming them, saying loop through all the orders one by one. I got a response stream .write async, so I'm streaming these things as I'm processing them. So there's the streaming. That's basically streaming them right back to the client. So again, I'm getting a nice, very fast performance story there by streaming this stuff back. So again, this gRPC, it's not hard to, it's not difficult to configure. What I found with it, it was a bit of a learning curve. I spent some time trying to understand what it was doing, how it worked. There was probably 4 or 5 places in my code that I had to touch. Nothing was hard in and of itself, but just to make it all work. Once you get it working, it's very nice. Now, I haven't done this yet, but my understanding is that Swashbuckle can now support gRPC as well, too. And there's also a tool, I'll show you really fast. It is called Bloom RPC. I'll show it to you right here. You can download this open source tool. This is also a tool where you can run and debug your gRPC code outside of .NET Core, outside of anything. You start your service, you open up Bloom RPC. There's not a lot to it, actually. And then once you do that, once you open this thing, it wants to open for me. Interesting. There it is. It's taking a good old time. Once that opens up, pretty much, you can invoke your running code. There it is right there. I didn't want really 20 instances of it. Maybe one would have worked. So again, you'll probably want to look at Bloom RPC. I just read an article. I found one where the author was showing how to wire up Swashbuckle as well too, to be able to see gRPC calls. So that's something to think about there going forward. So again, I think gRPC becomes a very good candidate. So I think what you'll probably end up seeing a lot too is people build out services. They will they'll build prototypes where they compare the performance of making REST-based calls with that of making a gRPC call. And you should try that too, I believe. And if a gRPC call is significantly faster, more efficient, then you probably want to start looking at gRPC as well too. I think the first time you build it out, it'll be a little bit time consuming. Once you do it 8-10 times, you'll understand it. You'll be able to get through it really quickly. So questions, comments, and all that. Again, so one thing I didn't tell you is we talked about this. We said, hey, you know what? We want to try to avoid these kinds of scenarios where one service calls another. These are not preferred, these direct synchronous calls. We said we might, if we have to do one, for example, here, then we probably want to think about maybe doing gRPC in this. We talked a little bit about
that's actually,
avoiding.
You know what?
Go right ahead, please.
That's a good question we have coming in here from Mr. Amazon, it looks like, asking what
Wow.
Yeah, what is that deciding factor that would take you from REST to gRPC?
That's a good question. I think the performance would be the big thing on it. If I can truly get a much smaller payload coming across the wire, and if I can get calls that execute in half, 20% faster, 30% faster, even 10% faster, that would be a compelling reason to start thinking about REST. Or about gRPC. I would think.
And certainly the streaming features adds another layer of capabilities there that might make more sense for folks.
Yeah, because many times when we're dealing with REST calls, our scenario ends up being that, hey, we're making a call and we're bringing back a collection of data. Give me all the orders for this customer, give me all the products for this category, whatever. So again, with that streaming capability, that should really, really increase our performance in terms of being able to really just stream back that data very quickly and be able to show it as well. And I think the nice thing about gRPC too is we do get a strongly typed contract on each side as well too. So I think that's a benefit as well too in some cases. So it's kind of funny. We went from a RPC model to a REST model, and now we're in many ways moving back to maybe more of the RPC model. What I did see in researching for the Cloud Native book, I spent probably almost a year just really immersed in open source technologies. And I'm here to tell you that in open source technology, Mr. Amazon would know this, gRPC is big, really, really big, very, very popular. And I think you're seeing a lot of it now too in the Microsoft stack, especially now that .NET Core has built-in support. I think what you'll see going forward is even better and better and better support built into the .NET framework for it, or the .NET Core actually for it. So great question. Other questions about client communication, queries. I am not client, but I'm sorry, query, where one service needs to call another, but it needs a response back. So wow, I got to wait around for that to happen. One thing I'm not showing you. Go ahead.
I was going to say there's some folks here that are asking, they're looking forward to talking more about CQRS architecture.
Okay.
But I know we have some discussion about that coming up. I know we also want to get into little Kubernetes here at some point.
Yeah, let's see what we can do. I'm gonna stream out a little bit here. I'm going to tell you this though, and we'll see this shortly. We're going to see one thing. We're going to see many times when. Just keep this in mind. If the shopping basket service needs product catalog data, needs to do a product lookup, wouldn't it almost make more sense to put a subset, a read-only copy of product catalog data right in the shopping basket service, so that way we can avoid this lookup completely. The data that shopping basket needs for product is already here. It's a small subset. It's denormalized. We'll talk about that in a while. It's very common to put what's called a read model, also known as a materialized view pattern, a read model of that data right in shopping basket so we can cut out that extra synchronous call, and then we can put some kind of mechanism in the background so we can keep this little read model in sync with the data that product catalog has. We'll come back to that.
All right.
Talk a little more about this. I want to close off messaging. I want to talk a little more about these. We talked about queries. What about commands and events? What happens with commands? I am the ordering service. I created an order. I need the shipping service to ship it. I need to tell it that, but I don't need to wait around for it to happen. And I don't really care when it happens. It just needs to happen. Or what about events? When something has happened inside of me as a service, and I want to, if you will, I want to basically let others know about that event. Commands are really key. It's really a simple relationship, really. It's a producer-consumer relationship. Here's the producer. It needs to perform an action, or it needs another server. It needs the consumer to perform an action, but it can basically just tell the consumer. It can fire and forget. It doesn't need to wait for the consumer to complete it. So again, this would be an ideal situation for a command right here. Typically here, we're going to make this asynchronous. We're going to have the producer pushing commands into the queue, and then the shipping service will pull each command out, open it up, and actually create that or ship that order on the fly. So again, the ordering service, it just pushes in shipping commands into the queue. Each shipping command has everything inside of it, what needs to get shipped and to whom, and the shipping service can pull out of the queue and process. Again, we're decoupling these things. Ordering doesn't even know about shipping necessarily. It just needs to push that command into the queue, and the shipping doesn't have any dependency on ordering. It depends on the queue. Typically, we're using queuing technology in here. It would look like this. I think most of you have seen queues. A queue is simply an intermediary construct through which a producer, again, this could be our ordering service, pushes a message or a command, and then the consumer, this could be our shipping service, can basically pull those commands out as needed and process them pretty much. So there's a point-to-point messaging pattern. Here we guarantee that each message is processed by at least one consumer. So even if service 1 pushes the message into the message broker, if service 2 here, if they're not working, that's okay, because the queue maintains that message until one of the services pull it out and successfully process it. So we're not going to lose that message. Again, we can scale out one side without scaling the other. We could have maybe .NET Core on this side and Java on that side. We can do that, again, because we're both dependent on the queue. And even the consumer doesn't even need to run all the time. The consumer can run sometimes and process messages when it needs to. What about events? Another scenario. So here we have the proverbial publish subscribe method, right? Here's a shopping basket. It's the publisher. You check out. You say, I want to buy these 5 songs in the checking, and I basically check out. So what happens here pretty much? The shopping basket says, you know what? You send a checkout command. Shopping basket goes, I got a checkout method here, but I can't really do much because I'm a shopping basket. I don't create orders. I don't affect inventory. In fact, what I do, I basically publish a checkout event to our message broker sitting in the middle here. We'll call it our event bus. And this could be RabbitMQ, it could be Azure Service, or whatever I plugged in. I publish a message into it, okay, an event. Inside the event, I have everything about that particular checkout. The songs the user wants to buy, who the user is, everything about it. And then I forget about it. I'm done. And then here, the ordering microservice and perhaps the inventory microservice, they subscribe to a checkout event. They care about that. So when one gets placed into the event bus, they subscribe, they pull the event out, and each can get a copy of that event, and they can act upon it accordingly. So again, we have an asynchronous relationship here. Shopping basket does not know about ordering or inventory, and these two do not know about shopping basket. They all depend upon the event bus abstraction here in the middle. Typically, we use topics when we're doing this. A topic is really interesting. We can push different messages into the topic. On the other side, we have subscriptions. So here's a price service. It has a pricing subscription. The discount service has a discount subscription. Here's the logging service, has a logging subscription. So as we push messages into the topic, we look at metadata, and then the topic figures out which particular subscriptions get a copy of that message. So if that message is about price, Then we basically push it into the price message, and we push it into the logging, because the logging rules is give me all messages. So then the price and the logging service get a copy of it. If that message is about discounts, well, then the topic pushes it into the discount subscription and pushes it into the logging subscription, and then these two. So again, we have the ability to push in multiple messages and segregate those messages based upon metadata in the message so that one or more subscriptions can act upon those messages. This would be this is how a topic works pretty much. Here's a scenario here. In fact, you can see pretty much in the application that we give you, we do have an event bus. It basically is using topics. You can see, for example, here, I'll show you an example. The shopping basket publishes a checkout event to the event bus. The ordering service subscribes to the checkout event. It creates the order. Then when the order is done, the ordering service publishes an order created event, and the shopping basket service subscribes to the order and created event, and at that point, it can basically clean up the shopping basket. And what we're doing here, we're currently we're actually building out a transaction. You're going to see we're going to do the payment and shipping eventually as well too. I'll talk about that in a little bit. So this would be an example here. I'll show you how it works in code. Quick example though. I bought a book about maybe 6 months ago. I bought a book from a company called Pact. They sell books. You probably have seen them. So I bought this book. It was $10. I basically chose a book, put my credit card information in. I created the order. This is what I got back. It said, thank you, your order has been processed successfully. Then it said, thank you, your order has been placed. And then it said, your order number is this. And then it said, you'll receive an email confirmation shortly at this. So I thought, well, wait, it's been processed, it's been placed. I'll receive an email confirmation shortly. So then I began to think, when I submitted this order, is it really processed? What if it's more like this? What if we check out in the shopping basket, right? And what happens here, the shopping basket publishes a checkout message to the event bus here. That's fine, and forgets about it. Then the ordering microservice subscribes to that checkout event, grabs it, it creates the order. Then the ordering microservice says, I'm going to create an order created microservice here, or rather an order completed. I'm sorry, it creates an order completed event when it's done. So again, it receives the order, creates the order, it publishes an order completed event back to the event bus, and maybe the shopping basket service, it responds or subscribes to the order completed event, grabs it out, and at that point, it cleans up this underlying shopping basket. So you can kind of see the little dance that goes on here. So when you submit an order to Amazon maybe, or to Pact or anybody else, good chance that order is really not processed. It's submitted. We present the illusion that it is. Thanks for the order. We'll get back to you soon. And what I got back from Pact about a minute later was this. It said, thanks for completing your purchase. Here's the details. So this came back 2 minutes later or whatever. So pretty much that kind of told me that when I first submitted it, we had to go through that order creation process. So Pact probably has a set of services, microservices, and again, that process took place. And when it was done, I got this back right here. Let's look at an example of that in code, and then we'll take a quick break. So we have in code, we have a couple of things going on. I'm going to, let's get out of the gateway here. So we have a shopping basket service here. And in my shopping basket service, we have a domain folder with our business services class. And in our business service, close everything else for right now. We just need this. Let's close all but this document. So here's our business services class. This is our domain business class. If we go down a little ways, you'll see that we do have a checkout. It's kind of hard to find. Here's my checkout event right here. It's a checkout event. This will get basically invoked when the user wants to check out. We'll step through this. We're going to end up here. We're going to basically create a checkout event, and then we're going to publish a checkout event here. Now, my ordering microservice is very interested in that checkout event. So in the ordering, what we're going to do, we have an events folder, and we have a checkout event handler right here. So this checkout event handler is going to get invoked by that checkout. And this is going to actually go through and create the order. I'll put a few choice breakpoints in here we can stop at. This will call the command handler. This will down here. Then we're going to create an empty cart event. Then we're going to circle back to the basket services. And we are going to empty. We have an event folder here. And we are going to empty our shopping cart right here. So we'll step through this. I'll show you what it's doing pretty much. So we're going to basically start with basket. We're going to create a checkout event. The ordering service is going to process the checkout event, create the order. Then the ordering service is going to create an empty cart event and publish it. And then back in the shopping basket service, we're going to subscribe to that empty cart event, and we're going to empty the shopping basket at that point. Once the order is created, that gives us a green light to go ahead and clear out the shopping basket. We no longer need that entry in there. And what we're going to do too is we're going to put a breakpoint in the actual plumbing of this thing. So here, if we go to building blocks, we have an event bus folder. The event bus folder has a implementation. Here it is, service bus subscriber. Notice again, the application talks to event bus subscriber. That's what both the service, the shopping basket, and the ordering service talk to this abstraction, this interface. We plug in the service bus event bus subscriber, and then basically when we invoke a method on the event bus subscriber, it fires up on here. Service bus is kind of interesting. It has this event loop, this callback. I got some breakpoints set in here. So let's run this. Run the application, give it a second to come up here. Well, this is happening. Let's look at this here. We'll take another short break. I want to come back. I want to close out, talk a little bit about data with you guys, about distributed data. We'll touch on CQRS as well too. And then about quarter of the hour, give or take, we're going to turn things over to Manu, and he's going to talk a lot about Kubernetes and a lot about being able to orchestrate these services in Kubernetes, and talk about some really cool things like service meshes as well too. So we should be running this here. Give it a second. Keep in mind we're running quite a bit of stuff on the computer. We're running 5 different services right now. So what we got running on here, I have got, this comes up here. So this is the API gateway. Notice again, we're exposing Swagger off it. You can see in the API gateway, we have, here are all the endpoints. These are the endpoints in the API gateway for the back-end shopping basket service. Everything goes through these. We can see we have a get all baskets, a get basket by ID, so on and so forth. The catalog service, these are the endpoints for the catalog service in the gateway. These will all behind the scenes invoke the actual back-end catalog service. And here are the endpoints for the ordering gateway as well too. Also have a UI. That should be up here. It is here. Kind of a corny UI. We call it retro turns. These are a bunch of old songs. If anybody remembers way back to the MBC Music Store, that was the reference application we have. We took that, and that became our online music store. So some of the songs are still in there. So here are the top selling. Let's pick a song. We're going to pick Carry On. I didn't make these up. I think this is a Crosby, Stills and Nash song, maybe. Come on. Well, let's see what's going on here. All right, are we not going to care? We stop at a breakpoint? What's going on here? I love it when you practice this stuff and you finally do it, and now we're getting some kind of craziness. What's going on here? Huh, don't know. Let's try. There it is. Finally. Okay. That's not good. That's kind of a long time. Usually it's instantaneous. So here's the song Carry On. Oh, this is Chris Cornell. I was wrong. Let's add it to the shopping cart here. We'll add that. I have fear in the background. Up fast. Oh, here's a problem. Look what's going on. Let me guess. Spiked at 100% CPU, I'll bet, or not. Why is that? What's killing me on the back end? Yeah, you can see something that's going on my computer that's not so not. Here it is. What's going on back here, dude? Microsoft Edge? Jeez. I have no memory. What's going on? Let's get. Oh, it's the streaming. That's what's killing it. Okay, guys, this may not work so well. The streaming is just killing my computer. You can see it's processing. So let me just walk you through what happened basically here. Unfortunately, we can see this, but if we could run it, we had decent bandwidth. What happened here pretty much is we would add the cart, add this item to the basket. It would check out. The checkout would invoke the event. It would basically publish the checkout event. That would get pushed into the message broker. The ordering system subscribes to the checkout event. It would grab that message, open it up. We have a checkout event handler that would open that message. It would take all those songs. It would build that order. And when it was all done, it would basically say, I'm all done. The order's built. Then it would create an empty cart event, putting the cart ID and the correlation ID back into the event, publish that event, and then the shopping basket service would subscribe to it, grab the event, open it up, and again, here we go, 20 minutes later. See, this is probably not going to be a good story here. I don't have any memory on my computer, I guess, unfortunately. It looks like not getting a good story. Okay, so let's take a break. Questions on that? We've been going. Maybe, hang on, this might work. Let's try. All right, submit order. Let's see what, I'm always hopeful. Let's see. Okay, here we go. We are in checkout. We checked out. What is this doing here, by the way? So we checked out here basically. We create the event here. I'm going to F5 into the event. This is painful, isn't it? So we're building a checkout event. In this code up here, here's what we did pretty much. We said build the checkout event. Notice what's inside here, okay? In the checkout event, in the order information model, so we build the event right here, and here we're going to send it. If I open this up, you can see inside the event is everything you ever wanted to know about the event. Here's a shopping basket ID, the checkout ID. We got one line item in here. This is going to be that song, whatever we chose. It was Chris Cornell, Carry On. The total is 99 cents. Here's the payment information from the user. The buyer information. Our buyer is going to be Bernardo Prince from Ohio. So we're going to publish that event. We just did that. Let's see what happens here. See how slow this really is. Okay, this is good. Here's our event bus. Here's the pump. It got that message. Okay. This is actually inside right now of the ordering. So the ordering grabs the event. It's going to decode or convert the actual body of the message. And now it's going to call the event handler, which is it calls this, let's go down here. It calls the checkout event handler. You can see it right here. We're going to pass the message in. Here's checkout event handler right here. This is kind of an interesting process here. What we do is we get the message. We're going to basically, we basically deserialize it. We build all the information we need. We call the command object, because again, we're doing CQRS, the command object, we'll step into it. It pretty much here, it builds everything we need here. I'll put a couple breakpoints back here. This will actually end up back here. This writes the order out to the database, both the relational, we'll talk about, and then, we just fired the empty card event. So now we're back in the message broker. He is saying, here's an empty cart event. Please handle it, shopping basket. And the shopping basket, the empty basket event handler, shopping basket grabs that event. It's going to deserialize it here. And it says, hey, you know what? Here's a shopping basket I need to get rid of. And here's a correlation token that's always follows it around as well too. So again, sorry for the performance on here. I think the streaming software is, is second memory, but hope that helped. Let's stop here. Let's take a break. Let's come back in 10 minutes, talk a little more about data, and we'll get into to Kubernetes, and we'll get into orchestration.
All right, sounds good. And we'll see you back here in about 10 minutes, friends.